operate the MR machine, right? So how about a housekeeper?
No.
What level are they though?
Level one.
Level 1, right? So anyone who potentially interacts with the MR environment has to be trained. So I don't know if you guys do, when you do your clinical rotation, oftentimes my previous students, they had to do yearly training, and so before they started their clinical times, they had to do whatever the hospital requires their employees to do. And oftentimes one of those courses is MR safety, right? So that's for nurses that come and give medication to our patients. That's for housekeeping, transport, all that, right? They have to be at least level 1. And then everybody else is considered non-MR personnel, right? Okay, what is translational force?
Isn't that the force that like, it's like causing like metal to get drawn towards
Absolutely.
the magnet?
Right, and the closer you are to the magnet, is the translational force greater or lesser?
Greater.
It is, the closer you get. How about an itty bitty small ferromagnetic object? Does that have great translational force?
Mm-hmm.
It does not, but it still has translational force, right? Okay, so why is the magnet always on? What kind of magnet is it?
Superconducting.
It is a superconducting magnet. So what is superconductivity?
It's the ability of a coil to sit in hydrogen and maintain electrons without having to be plugged in.
Yes, so
What is the
zero
cryo?
electrical
Well done.
resistance.
Yeah.
Yeah. There's no electrical resistance. Why? With superconductivity. Why is there no?
The cryo.
Super cold.
Yeah.
It's cryogen, right? So there's a cryogen. We submerge our niobium titanium coils in a cryogen, removes electrical resistance, so we can ramp up. Whenever you hear the term ramping up, that's building a magnetic field. Ramping down is diminishing a magnetic field, right?
Mm-hmm.
We can plug in that magnet, ramp up the magnetic field, and then we can unplug it, and those electrons stay spinning through that coil. Magnetic field remains. Okay, is it a cheap thing?
Ooh.
No. Why is it so expensive? What's one of
It's
them?
like liquid hydrogen or something.
Right,
like
liquid hydrogen, obviously hydrogen, not a liquid on this planet, it's expensive,
Mhm.
okay?
Like negative 200 some degrees.
It's 4 degrees Kelvin, it's as close to absolute zero as we can get, we believe, right? So super, super cold. Okay, signage. It shouldn't be around MR in any way, shape or form.
Oh,
Red.
Red, or MR unsafe,
Mhm.
right? So then, what's the yellow one?
Caution.
Caution.
Caution, what does it mean to us though? That equipment is,
Like,
Either or.
Potentially
Yeah.
safe
Yeah, it could
and
potentially
zone
be-
3, but not.
so conditional,
Yeah.
right? That's what we call it. It can go in there if you meet conditions,
Like
right?
aluminum, right?
Yep, usually on the floor, when you guys start your rotations, usually on the floor, they'll be, okay, nothing can go beyond here. We're gonna talk about that now, the 5 Gauss line. MR conditional ventilators often will have their own marked area on the floor, right? So if you see that yellow triangle has MR in it, it can go in zone 4, but only with conditions. Typically those conditions, it needs to stay away from the middle of the bore, right? It needs to stay at the end, the foot of the bed is kind of what we call it. And then it can go freely into zone 4, what is that?
Emergency.
MR safe. So what's something that's MR safe?
Plastic.
Plastic, wood, aluminum, that kind of thing, right? All considered MR safe. Okay, so the magnet is always on, but can we turn off the magnetic field if we absolutely have to? What's that
Yes.
called?
Quench.
A quench. And what is a quench?
You're,
Press the button.
yeah,
Push
taking
button.
out the liquid hydrogen out and ejecting it
Yep.
into the air.
Vents open, liquid turns to gas
Hopefully.
almost instantly.
Yeah, hopefully, yeah.
We quench it, right? So is it safe to be in the room in zone
Ooh.
4? Why not?
Because some doors don't open the correct way.
It sucks the oxygen out.
Right, the valve, if we don't know for sure if it's gonna open, the helium will replace, or the hydrogen, or helium, will replace the oxygen and you could suffocate, right? So that's why generally we want the doors to open out. But is there hard and fast rules as far as MR safety is concerned, there's not, so you'll see them multiple ways. All right, so we will pick up with where we left off, which is shielding. So, the main magnetic field is pretty powerful. We've talked about this. 1 Tesla, not very often will you see 1 Tesla anymore. 1.5 Tesla and 3 are the most common, but up to, in this country anyways, 7 Tesla. So the field isn't contained within the bore. It extends in 300 degrees outside of it in all directions. We call that the fringe field, right? So the fringe field, especially like a 7 Tesla magnetic field, it can extend for quite a distance. Generally speaking, most facilities aren't going to have a large enough room to house a magnetic field of that strength without some kind of magnetic shield. So, current standards in the United States state that your field has to be restricted to an area within zone 4 of 5 Gauss. So every person in the general population, regardless of medical device that they might have implanted, doesn't matter, they can be exposed to a field of up to 5 Gauss, even people with non-MR conditional pacemakers. 5 Gauss. So somewhere within zone 4, there has to be a demarcation that says if you cross this line, you're going to start feeling the effects of a stronger than 5 Gauss field, right? So the center of the bore, what's the unit of measurement we use for that magnetic field? Tesla, right? So the fringe field that extends out from the main magnet is Gauss. So how many Gauss in a Tesla?
10,000.
10,000 Gauss per Tesla, right? So we measure the fringe field in Gauss. So you have your 5 Gauss line. The closer you get to the magnet, the magnetic field that you are experiencing is getting stronger and stronger and stronger the closer you go, right? So in order to contain that powerful magnetic field in a room, we use magnetic shielding. There are 2 different kinds, passive and active. We're going to talk about both of them. So the first one is passive shielding. Passive shielding is used primarily in research settings for incredibly powerful magnetic fields, not used clinically. So I'm talking 14, 15, 16 Tesla magnetic fields. We'll use passive shielding. Your everyday normal clinical magnet will not use passive shielding. They'll use active shielding. Very large magnetic fields tend to use both active and passive. Passive shielding is, and I'm not even kidding, sheets of galvanized steel that they put in the walls of that room. So why? These sheets, they're metal, right? So they are easily going to become magnetized. You put a nail on a magnet, right? You rub it around on that magnet, all of a sudden that nail becomes a magnet, right? Those nuclei are very susceptible to being aligned and forming a magnetic domain just like we do in the body. They just do it more easily and they hold on to that magnetic field for a longer period of time. So what happens with all this metal, they feel the effects of the magnetic field. The electrons that lie within that metal line up and another magnetic field is produced in the metal and it works in opposition to the main magnetic field, right? So if you have a north-south and south-north, those magnetic fields are going to act in opposition. It contains it in the room, right? It basically makes it a little bit smaller. That's what it does. So what are some disadvantages, obviously, to putting a bunch of steel plates in your walls? It's incredibly heavy, right? And it can be expensive. So passive shielding, metal plates in the wall, right now in this country, that's reserved for very, very, very large magnetic fields in research settings. Your clinical shields are going to be what we call active shields. So what is that? It is yet another superconducting magnet. The coils of your shields, we call them bucking coils, so they're bucking the main magnetic field. They are on the outside of the coils of your main magnet. So all of these coils are your main magnet coils, and then on each end of your magnet, you will have the bucking coils. So the bucking coils are yet another superconducting magnet. So what does that mean? The electrons spinning in the bucking coils are going in the opposite direction to the electrons moving in your primary magnet coils. So, the left-hand rule, did you guys learn that in physics?
I thought it was
Yeah.
the right.
The direction of the current, your magnetic field is produced 90 degrees this way, right? So then what happens if you have another magnetic field that's being produced with the current going this way? They're going to oppose each other. Does that make sense? So it's not as strong, but it's still a pretty strong superconducting magnetic field that acts in opposition to your main magnetic field, and it contains it, right? It holds that magnetic field to a level of 5 Gauss, has to be in zone 4, to a smaller room, right? And that's what it's doing, it's just bucking it down, containing it to the room. All clinical MR magnets use active shield.
Does that ruin the performance of your machine though?
It can mess with it, but again, and we'll get there when we get to instrumentation, which is the next unit in the lecture, we can shim a magnetic field. We can try and make it more homogeneous. What the bucking coil does, if you get the opportunity when you get to your clinical site to kind of play with something metal in the magnet room, the openings on either side, put that piece of metal as close to the opening, like the plastic cover, as you can. You will feel that it has tremendous more pull than it does right in the center. And the reason is because that bucking magnetic field inverts right there. And so it makes it a little bit more stronger. You have multiple lines of flux that are basically added up right in that area. So it makes it a little bit more pull. You'll feel the pull more kind of right along the top of the opening than you will in the center of the magnet. It's just something you can feel.
Is the bucking coil stronger than the main magnet?
It's not as strong. It's still strong. Probably in a 1.5 Tesla field, it's probably 0.8, 0.9 Tesla.
What keeps it from not going in the same direction as?
It's how they put the current through.
Oh.
Right, so if you put the current through and you know that the current is going in that direction, you've produced a magnetic field in this way, right?
Yeah.
So they're gonna put the current into the bucking coils going in the opposite direction so that they produce that field that's gonna act in opposition. It's how the electrons flow. All right, so within zone 4, as I said, that 5 Gauss line should be clearly marked. It could be on the floor, it might be on the ceiling. I'm really interested to know the places that you go to around here, if it's all on the floor or if they have any on the ceiling. I've never been to a facility that has it on the ceiling, but I've heard of them. So in this picture I've kind of showed you, they actually have 2 lines. They have the 5 Gauss line right there, and then they have a 50 Gauss line. You can see it's getting closer and closer and closer to the center of that 1.5 Tesla magnet. And again, 5 Gauss and below, that anyone can be exposed to that and they will be fine. We won't have any issues with 5 Gauss.
Is the doorway the same? Like, cause the 2 that I've been into, it was the doorway that led in. Is that considered
the
the
doors
same?
open in?
Like that you just don't go past that door?
Oh.
Or is there other markings?
There
that-
should, generally speaking, by the door, depending on the size of your zone 4, the door might not have any. Usually that line is in from the door, but it might not be in every facility.
I haven't paid attention, like,
Yeah.
I wasn't looking for lines.
Yeah,
I just knew
so-
not to go.
And
past
sometimes
those.
you can see on this, it's just a different color of linoleum. So I've seen that too. They're like, well, as long as you stay on the brown linoleum, you're fine. As soon as you move over into the blue, you're within the 5 Gauss line. So it's just a different color of linoleum. But some will have literally red tape on the floor, which is the 5 Gauss line, and it says do not cross. So I'm interested to see what you guys see when you're out there. Okay, the spatial gradient. I apologize that I have hair in my mouth and I cannot get it out. So, throughout the course of this year, we are going to be talking about gradient magnetic fields. That is not this. They use the same word, but I want you to, in your mind, I'm not talking about the gradient fields that are used for spatial localization. This is its own beast, okay? So, the spatial gradient basically is defining at any point the strength of the field that you will experience with a given magnet. So the spatial gradient of a magnet is where in that room a person would experience a particular magnetic field strength. So why is this important? Because certain implanted devices can kind of stand up to a spatial gradient of say 0.7 Tesla, but not 0.73 Tesla. And so if you have, say, a little 0.5 system, there might be somewhere, because we know there's hot spots and cold spots, right? There might be somewhere where they would experience that high of a spatial gradient, kind of where in space this particular strength magnetic field is, and so they can't go in the room, if that makes sense. So every system manufacturer is going to have a spatial gradient map. So you can see where in the room the magnetic field is whatever potential strength that maybe you're trying to avoid. The variation with distance is known as the spatial gradient. The closer you get, and we've already talked about this, the stronger the field you will experience. The farther away from the center of the magnet, the weaker the field you will experience. So you can see this map. They have the meters marked out, and then where you are, so many given meters from the center of the magnetic field that you will experience if you get that close, right? So at 5, it's 0.1 millitesla, 0.3 millitesla. The closer you get, the stronger the field that you're going to experience. So we kind of talked about that attractive force, that translational force, right? It's dependent on the spatial gradient. The larger the spatial gradient, the greater the force. So if you have a very powerful system, let's say this is 3 Tesla, right? Then the force you'll feel on metal is going to be significantly greater at 2 meters than at 4 meters, right? And we can calculate where in the room or how strong of a force you will feel with sorry, my kiddo is sick, with a given field. So it is measured in Tesla per meter, so you can see with this particular magnet, we're doing millitesla. So you're not experiencing a great spatial gradient the farther you are away. The closer you are, so our patients, we're gonna put right in the middle, they will experience the strongest spatial gradient. Okay, so this is what I was talking about. Because of the bucking coils, it brings that field in. And so right around the topmost part area of the magnet, it's going to be the strongest, right? And then as you move out, because the bucking coils are restricting the field, it gets significantly less. If you didn't have shields, then these numbers would be infinitely higher, right? Especially if you have a powerful, like a 3 Tesla magnetic field. So this kind of talks about the pull of your true magnet right in the center. It's going to be greater. As you go out, it gets weaker and weaker and weaker. It drops off significantly. So every system should have a spatial gradient map. So you can see where in that room, where, you know, as you get closer to the magnet, you can see what those patients will experience depending on where they are. So why is this important? Certain places, say an implanted device is kind of a no-go, patient can't have an MR. There are certain facilities that will scan certain devices if they can keep the patient out of the areas where the spatial gradient is stronger than what that device can withstand. So for example, they'll put them on a gurney and they'll wheel them in and they'll make them lay perfectly flat because they know if they lift their heads up and they start cutting lines of flux that are at a greater spatial gradient than over by the door, then that implanted device might be affected. So they'll try their hardest to keep them flat, and you can see, as long as you're right there, it's 3 Tesla per meter, right? Up here it's 7. So they'll do what they can to try and keep the patient away from that as best they can. I think that's crazy and insane, right? Because whose license is on the line if somebody gets yours, right? And so I don't think that you should do that, but I want you to know that there are some facilities that do, and they shouldn't. But you should have your map. Wherever you go, they should know where the spatial gradient map is, and again, it's for implanted devices. All right, so these are those bucking coils. So you'll be able to see where the field inverts And that's what causes this area to be so strong on the ends. Let me play this for you. So these are the bucking coils out to the side, and they're acting in opposition to the main coil. Do you see how it inverts right there? Do you see how it's inverted and then it goes in? That's why right around the bore, it's the strongest, because on either end, where those bucking coils invert as they try and contain the field, it's more powerful because the lines of flux add up right in through the openings. But you saw how big the field was before it was shielded, right? That would be how big, well outside the door. So by acting in opposition, you have two magnetic fields acting in opposition.